here, getting away from the Earth a little bit. All the chapters so far have been dealing specifically with the planet Earth. We're going to look a little bit beyond well, actually not a lot, or a little bit, but a lot beyond the surface of the Earth here. We're going to go out into the heavens, looking at the solar system. This brings about a new area of study called astronomy, the study of God's creation beyond our atmosphere. Basically anything not on the planet. That's what astronomy is. Astronomers are those people who study things not on the planet. And there are lots of different types of astronomers. There's the kinds that observe the planets. Some focus mainly on stars. There's also astrophysics, how things work in space, because gravity, well, it's just not as concentrated in some areas, and we'll talk about that a little bit later on in this chapter as well. The structure of the solar system. From the earliest days, man has been looking out at the sky, and pretty much all the early writings, we see references to stars. Even really early on, we see references to some of the planets. As they are close to us, we can actually see them with our eye. They look different. They behave differently than the stars, and so that set them apart. People noticed, paid attention, started observing them more closely. The solar system includes the sun and all natural objects that orbit it. We refer to our solar system as the solar system. If you watch a lot of science fiction or read a lot of science fiction, it sometimes gets shortened to Sol system, just the S-O-L there, just to make it sound a little bit distinctive, a little bit different. The orbit of objects simply means to circle around due to gravity. There may be some other effects on it, but the gravity of certain objects is what really affects them. The moon orbits the Earth and stays in its orbits because of the Earth's gravity on the moon, acting on the moon. The planets stay moving around the sun because the sun's gravity acting on the planets. And gravity is directly related to the amount of mass. We will, again, later on in the chapter, we will look at an equation that fleshes out that relationship a lot better, or a lot more specifically. Aristotle was one of the Greek philosophers many centuries ago, around BC 300s. And he popularized the idea of the universe as being geocentric. You may recognize the word geo there. That simply means, geo means earth. Geocentric means earth-centered. And his view of the solar system had all the stars and planets orbiting the earth. Many people preferred his view because it made sense to them. They didn't realize that the earth was moving at the time, and therefore his observations made sense. However, the people who studied such things weren't exactly satisfied completely with that answer. There were questions that were raised as a result of what they observed. Even during Aristotle's time frame, around BC 280, we have Aristarchus. He proposed that the Earth orbits the sun, even that early. But ultimately, Aristotle's philosophy won the popular vote and continued to be popular for many centuries there, even being built on by Ptolemy, who was lived in Alexandria, Egypt around AD 150. And he was an astronomer. He expanded on Aristotle's geocentric view. He studied the stars, he studied the planets, he studied their relationships, and he took Aristotle's basis that the universe is geocentric and some of his other related stuff and built on that until it sounded like a really good theory. He wrote a book called Almagest. Ptolemy used detailed diagrams, mathematical data to explain the universe. He really did a lot to try and put it on a scientific setting, basing his observations, having math involved. He included accurate predictions of the planets' locations for many centuries, even though the core to his idea was ultimately wrong. That didn't take away from the work he did. The work he did was not ultimately reliant on whether or not the universe or the solar system was geocentric or heliocentric, sun-centered. It was based off of his observations. And even though his core idea was wrong, he still did a lot of the math correctly. He still had a lot of good observations. And he was able to make good predictions. He noticed that The motion of the planets confused him a little bit, though. He would notice that the planets do not move through the sky in a straight line, which the sun and the moon appeared to do. In fact, every so often they appeared to reverse direction, travel backward for a while. And actually, we still kind of use the terms that he coined or that he used there, such as retrograde, which means to go backwards. So to explain these motions, he taught, or he came up with the idea that the planets move in little circular orbits within their larger orbit. And on page 303 in your books, you have a diagram depicting it. As a matter of fact, this was such a convincing argument because it made sense of a lot of the observations that it was carried on for many, many centuries, even though when we realized that the Earth was not the center of the solar system. This observation and this explanation of the observation made a lot of sense. There were still problems. We'll get to that later. So Ptolemy, the Egyptian astronomer, expanding on Aristotle's, and again, those ideas kept going for many, many centuries, even to the point in the Middle Ages, we eventually get to Nicholas Copernicus in 1473. Well, that's when he was born, was 1473. And he was a Polish astronomer, and he really proposed a heliocentric system idea here. Heliocentric simply means sun-centered, and this was very controversial at the time. And the reason was not because of the science. Like I said, Aristarchus, even back as early as 280 BC, said that it's a good theory. The reason it was controversial was because this area of science, specifically Aristotle, had become politicized. One of the popes before Nicholas Copernicus said that Aristotle was right, and the beliefs of the early Catholic Church said that if the Pope said it, then it was coming from God. So it was seen as God was saying that Aristotle was right, and if you said that Aristotle was wrong, you were saying the Pope was wrong, which was in a sense saying that God was wrong, and they didn't like that. And the Pope actually, at the time of Copernicus, actually threatened to excommunicate him, which basically means that he could not get to heaven. He would go to hell, and there was nothing he could do about it. So Copernicus quietly proved the point, actually. He gave in to the political peer pressure at the time and said, fine, whatever, I take back everything I said. But he also quietly kind of said that the truth will come out. The Catholic Church is squashing Copernicus right now at his time, but eventually the truth does come out, as we all know today, taught from even when we're little, that the solar system is heliocentric, proven over and over and over again. Galileo Galilei agreed with Copernicus, built on his ideas, and really fleshed it out using some of the first telescopes that were really useful as far as seeing things out there that had not been previously seen. Let's see. The most important evidence was Galileo's discovery came from his observation of the planet Venus. Galileo observed that Venus has phases, just as the Earth's moon does. However, according to the Aristotle version of the solar system, that would mean certain phases of Venus we should never see, such as a full-on where we can see the entire side of Venus. No more than half of Venus should ever appear illuminated, according to Ptolemy's research on Aristotle's foundation, that we should only ever see like half of a Venus. However, Galileo observed full Venus, totally illuminated from the sun. And that was really only made sense if it was not a geocentric, and it did work with a heliocentric model. And by the time Galileo comes on the scene, quite a while later, it was a couple hundred, almost 200 years later, and the political fervor had died down about this. The science was allowed to come out a lot better and be communicated a lot better, and Galileo really brought forth and did a lot to support Nicholas Copernicus's original idea of the heliocentric solar system. Then we also get some other scientists later on. Johannes Kepler, and excuse my spelling, I misspelled the word Lutheran, I apologize. My fingers mistyped. And his goal was to find mathematical harmonies in the mind of the creator. And he did that by studying the solar system to a certain degree. Tycho Brahe, a Danish astronomer, kept very accurate records of his observations, and this all led, the work of Kepler and Brahe, both led to support for Galileo's observations and the resulting idea of the heliocentric solar system. So now that we've got all of that in place, there was still one problem. The way the planets moved didn't really fit the current standard for both of the models, whether it was geocentric or heliocentric. Remember back with Ptolemy, he brought about that idea of the planets moving in circles around the sun, and then they were also moving in circles along their orbit. And this explained a lot, but there were still problems with that explanation. First off, one of the things was that they assumed that the planets moved in pretty much a perfect circle around the sun. Well, partially due to some of these people that we've mentioned before, we come to find out that they're not moving in perfect circles. They're moving in what are called ellipses. This is a symmetrical oval that has two focal points. One of those focal points is the sun. We'll talk about that more with the laws of planetary motion. But there's two focal points, and it's this circle. There's a lot of other mathematical relationships that go into this idea of ellipses. We're not going to worry about that for our question. Just know that it's this symmetrical oval, and it has two focal points, and it's not dead center. So Kepler did a lot of observation of the planets, and when this idea of ellipses first gets used there, it starts making sense of a lot of things. And Kepler formulates three laws. Now they're actually not in the order that he originated them. For whatever reason, at some point in history, they got flip-flopped, and I believe he actually discovered the second one, what we call the second law, first. Doesn't matter the order. Just so long as we understand that there are three laws. The first law, every planet orbits the sun in an ellipse, which we just talked about. The sun is one focus, which you see on the screen here, and an empty point in space is the other. So far in all the studies, we have not seen a second physical object at a second focus point. It always seems to be empty space. B, the second law, as a planet moves closer to the sun, it travels faster, and as it moves farther away, it slows down. Basically, this is a description of why the planet does not crash into the sun as it gets closer. It actually speeds up a little bit, and then as it moves further away, it slows down. This idea behind the second law has been used in many, many movies and motion pictures. I remember one of the first times I was introduced to it was actually in an old Star Trek episode of Star Trek. Where they slingshot around the sun. Basically, they use the sun's gravity to accelerate their speed. And as the planet gets closer to the sun, we do know that the gravity does get stronger because the distance is reduced, and that could actually potentially speed up the planet, giving it enough momentum to move around the sun. Now, in reality, there's no real difference in time as far as how we notice it. In the movies, they always used it to go backwards in time and go back to a different age. But that's why we call it science fiction. So in the orbit around the sun, we have two points that have name. One is perihelion. This is the Earth's closest point to the sun, which on our diagram here would be way off to the left. And aphelion, which is the most distant point from the sun, and that would be way off to the right. The third law, and this has to go with its rotation around the sun, or its orbit around the sun. The farther a planet's average distance from the sun, the longer its period. And the period is the amount of time a planet takes to complete its orbit. For Earth, that's 365 days. For Mercury, it's significantly shorter. I think it's somewhere on the level of 80 days, or right around there. And Pluto, which technically isn't a planet right now, I know, but they're still working on that. It's much, much, much longer, on the level of several Earth years, not measured in Earth days. And then we also have some measurements out here, and that is the astronomical units. Probably one of the two main measurements that we will hear dealing with space. The other being a light year, and we'll talk about that at another time. But the astronomical unit, abbreviated as AU, it's approximately the distance between the Earth and the Sun. Now, if you were paying attention, we just talked about the Sun rotating around the Earth, the other way around. The Earth rotating around the Sun in an oval, so its distance does vary. I've heard it rounded off to 93 million miles, and I've heard it rounded off to 94 million miles, because the average is actually somewhere in between. So that's the approximately distance between the Earth and the Sun. One of the big game changers as far as our understanding of how motion works and how things move in space was understanding gravity, and this came about as a result of Sir Isaac Newton. His observations of gravity and his descriptions of gravity helped us understand some of the questions that were still in place when Kepler came up with his laws of planetary motion. They explained some of the discrepancies that people were seeing. Well, why is it moving this way? Why does this one move that way? And it's really based off of gravity. And gravity is that force of attraction that exists between any two objects. It is directly related, well, I'll get to that in a second. The law of universal gravitation, as stated by Sir Isaac Newton, states that the strength of the gravitational force between any two objects, force, F equals G, gravitational constant, times the product of the mass of the first object times the mass of the second object, that product of the two masses divided by the distance squared from each of the object. And that distance is measured from the center of each object. And the gravitational constant is extremely, 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 extremely small. If I'm remembering the number right, because I don't think it's in our book, it is a decimal followed by 11 zeros, and then we start seeing numbers after that. I want to say it's like 0.11062, but my numbers might be wrong on that. And so it's really, really tiny. So the masses have to be really, really large, or the distance has to be really, really small too. The pen that may be sitting next to you, there is actually a gravitational pull between you and the pen on the desk next to you. And it's just so infinitesimally small, we don't see any result there. And it was several years after Newton did his studies that they were actually able to figure out the precise measurement of the gravitational constant. It took some very precise experiments that were set up in very, very delicate ways to figure that out, building off of what he studied. So yeah, gravity played a big role in our understanding of the solar system and why the planets move the way they do, how much gravity is affecting them. It's actually one of the reasons why I believe they discovered Pluto, was because there were motion discrepancies that led some to believe that there was a planet beyond Neptune and other bodies that are out there as well. So that interplanetary space, the space between planets, it is deemed a vacuum. Technically, there is stuff out there, but it is spread so far apart that for all practical purposes, it acts and behaves like a vacuum. And as such, we have to take precautions. Movement through a vacuum is fairly easy, but getting into the vacuum isn't so easy. We have to leave the gravity well of the planet Earth. With all these planets and the motions and everything, some people have often wondered about the beginning of the universe. And according to the Bible talks about God speaking everything into existence. That includes the sun, moon, planets, stars. People who have decided to use an answer that does not include God, they usually start from some point where there is an infinitely small, infinitely dense object. I don't know what other term to give it, but it's basically all the matter in the universe in this really, really tiny object. Think about the Big Bang comes from this idea as well. And it explodes outward, the matter spreads out over time, many, many, many years of time. Things coalesce, the gravity pulls them together, they start forming stars, planets, moons, asteroids, all those kinds of things that we find out there. Really, this is a nebular hypothesis, not including the Big Bang. It's after the Big Bang. It's when all the gas and all the other materials are out there and things start forming together. Just like we see when we look into the space, we see nebulas. So they call it the nebular hypothesis. And just to point this out, regardless of which explanation you go with, something has to be eternal, always existent. In terms of the nebular hypothesis, it's matter. Matter was always existent. Matter existed before anything else happened to create our planet. Some people have talked about a cyclical version where it expands, it contracts, it expands, it contracts, and it's been doing this for eons. We're just in a current set and have been for several millennia, according to these believers that we're in a period of expansion. So it's either matter or, if you believe the Bible, it's God. God is eternal, speaking matter into existence in a very specific way. So we see that here. And that brings us to the close of this particular section of chapter 10. Answer the science video question, and I will see you next time.